we just covered that we need an equation of a hyperplane in the form W transpose x plus bias equal to 0. So, let us discuss how we can come up with an algorithm and then prove the correctness of the algorithm. For this, let us define some variables. So, we form this vector xn as plus 1, that is the first coordinate, then we have x1 n, x2 n, dot 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 xm n, and I will say this is transposed. Okay, we have an m plus 1 dimensional vector here. Similarly, we form the weight vector w of n, which is b for the bias, that is in the first coordinate. Then you have w1 n, w2 n, so on, wm n transposed. So, these are m plus 1 by 1 vectors. Okay, so the n signifies that we are operating in online mode and we are getting these vectors sequentially at time n. So, the indication of the time order is basically n there. Now, so we have defined these two vectors. So, we define these of n to be the inner product between x and w. So, I would call this w transpose n times x n. Now, one of the claims which is obvious is for the perceptron to function properly, if you have a two class problem, these classes must be linearly separable. So, let us visualize what linear separability is, and this will help us to get an idea of what is happening, right. Let us imagine two distributions. We have two classes, this is class C1, this is class C2. So, if I can get a hyperplane that can separate these two classes, then they are the classes C1 and C2 are linearly separable. So, we can say that these classes are linearly separable if we can have a hyperplane that can cut through the region separating the classes. Similarly, if we have two classes that are nested like this, for example, and let us assume that this is C1 and this is C2. Obviously, we cannot have a hyperplane that can cut through the region separating C1 and C2. We cannot have a line that separates these two classes. So, in such a situation, we say that they are not linearly separable, which means you can have a curve that can go through this region and can separate the two classes, right. We assume these classes do not overlap. So, this is an important assumption. I think I should write it, that classes do not overlap. If they are overlapping, then this makes no sense. Okay. Now, coming to more concrete terms, suppose we consider inputs that come from a linearly separable class. Then if we have W transpose X greater than 0, there exists some W, maybe in the interest of notation I put W optimal. So, there is some W which optimal which we figure out, and if W optimal transpose X is greater than 0, this implies X belongs to C1 for all such X, and the other way around, if this inner product happens to be less than or equal to 0, then X belongs to class C2 for all such X whose dot product is negative or 0. Now, this is what we want, and this is obvious from the diagram that I had earlier. So, if you can visualize this diagram, I am just showing you this slide here. If you visualize this diagram, everything which is on this part of the hyperplane is C1, anything which is on the other side of the hyperplane is C2. So, we can kind of think about it. This equation is basically describing this geometry. Okay. Now, here is an algorithm towards getting the optimum value of W. Right? We have not said what is optimal. I mean, the optimality here is if we solve the problem of linear separability, then we say we have a solution, right? And that's so instead of optimality, maybe I think the right word is towards getting a solution to W. Okay. Now, let me state this algorithm in 2 steps. If the nth data point from the training set, that is x of n, is correctly classified by the weight Wn. So, there is some initialization, we will talk about this once we complete the procedure. So, if there is a weight Wn and then the nth data point from the training set Xn is correctly classified, then no correction is made to the weight vector in accordance to the following rule. So, I have W of n plus 1, this is Wn, that is I do not touch this, because it is already right. If W transpose n xn, that is the inner product of this weight with the data point, is greater than 0 and this data point happens to be belonging to class 1, it belongs to class 1, and of course you can imagine that the inner product between the weight and the data point is less than or equal to 0 and xn belongs to C2. I mean, statement, the first part of the statement would anyway imply the second part of the statement, but I have written this for clarity. So, I do not have to adjust the weight if it is lying naturally where it has to lie, right. If the point is lying on one side of the plane and it is positive and the inner product between the weight and the point is positive, it belongs to C1, else it belongs to C2, then I am already fine, I do not have to adjust my slope. If this is not, then we have to update a weight. So, I would say else we update the weight vector as follows. Let us see what this update rule is. Wn plus 1, that is the weight adjustment at time n plus 1, is a weight adjustment at time n minus some eta of n, you can also fix eta to be some constant, times x of n. If W transpose of n, x of n is greater than 0 and xn belongs to C2. So, I will write the other statement, I think you can, and then I will explain how this works. Wn plus 1 is Wn plus some eta of n xn if W transpose n xn is less than or equal to 0 and xn belongs to class C1. So, we have to update if we consider a situation where the inner product of the weight at time n and the data point is greater than 0, but the class to which this data point was belonging was C2 instead of C1. That means this value should, the weight that we had should be lowered, and therefore, I have to scale in the direction of xn. So, I subtract this quantity xn, I scale it with some eta. Similarly, if the inner product was negative or 0 and the data point was belonging to class C1, then I have to add this this weight, I have to add something to this weight aligned in the direction of xn, and that would be scaled by eta. So, there is going to be a plus sign here and there is going to be a minus sign here. So, you have to see this carefully how this works. Here eta of n is a learning parameter. Sometimes, or I would say most times, eta is a fixed constant and it is independent of n, and typically eta is a small quantity, and one can choose eta to be 1 also. So, we want to keep it fixed so that we do not want to complicate the dynamics of the algorithm, and for this reason we would like to keep eta to be fixed. So, I think this algorithm should be pretty straightforward, right. It is like basically balancing a pan, right. It is like balancing a pan. If weight is higher on one side, you just adjust it and put it onto the other side of the pan. So, this is basically the intuition behind this perceptron algorithm. Now, one of the key issues is, can we show that this algorithm converges for a linearly separable class. So, we will delve into the details of the proof. That would be our next step. So, if you just recall what I did just a minute back, I never specified the initial conditions. I just gave you the idea that you start with some weight and then I adjust the weight in such a way that I can go, I do not have to do anything if I am correct. If I am incorrect, then I just add or subtract the weight depending upon what the inner product was with respect to the data point. Now, let us fix the initial condition. Let us start with the initial condition that weight at time step 0 is 0. I mean, this is a all 0 vector. Now, here is what we have. Suppose W transpose n x n is less than 0 for n equals 1 to dot 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 and x n belongs to class C1. Right, if it belonged to class C1, this inner product had to be greater than 0, right. I can basically put this equality as well just to be consistent. So, there is an issue here, which means it is incorrectly classified by this weight at time step n. So, with eta equal to 1, we follow our update. So, what should we do? The weight at time n plus 1 is the weight at time n plus the data point at time n. So, I am considering this particular case when x n belongs to C1 class 1, but you can also consider the other case when x n belongs to C2 and then proceed with the weight update. So, that is without loss of generality, right. It is consistent. We do not have to worry about the other case because this will take care of it, because update will be changing if x n belongs to C2 and then the inequality flips the other way around. Now, W n plus 1 is W n plus x n. This is the update. Now, let us recursively unfold this weight at time n plus 1. This is a simple recursion. Now, if you do this, we have W n plus 1 is W n plus x n, then again expand W n is W n minus 1 plus x n minus 1, so on and so forth, right. So, if we do this, so we will end up with this on the right hand side of this equation. W n plus 1 is x n plus x n minus 1 plus dot 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 plus x 1 plus x 0, right. You have to take care here that W 1 is basically W0 plus X0, and W0 happens to be 0, and therefore this quantity is correct. Let us call this equation 1. So, I should remember these equation numbers. Okay. Since the classes are linearly separable, W transpose of n times x of n is greater than 0. I mean, there exists, since the classes are linearly separable, there exists, I would write it here, there exists a solution W naught for which W naught or W optimal, I will put it OPT here, such that this is true for all inputs x that belong to class C1, right. If I give you all inputs x belonging to class C1, since the classes are linearly separable, there should exist an optimal hyperplane such that this decision holds. Now, for a fixed W optimum, so instead of writing OPT throughout, I will just use O here. Do not distinguish, do not confuse the O with the 0. So, this is O. For a fixed W0, let us define a quantity alpha to be the minimum over all x belonging to C1 W optimum transpose x. Right, let us call this quantity as, let us call this equation as 2. Now, for the purposes of illustration, so we can put an index of x with time n indicating it is the time step when x is presented. So, I am okay if I can write this as xn and I put an n here indicating the time in which we are presenting this data point. So, multiply equation 1 both sides by W naught transpose, right. I did not indicate any time here because when I have an optimum hyperplane, the time does not really matter there, I am stopping at that point, right. So, deliberately the time index is not there for the optimum hyperplane. So, what we get is the following when we multiply equation 1 both sides by W naught transpose. So, just let us look back into the previous slide. So, we have this equation here, if you can recall. So, you multiply this equation 1 by W naught. So, when we do that, what we get is the following W naught. So, there is a bar here, W naught transpose times W of n plus 1 is W naught transposed x 0 plus W naught transposed x 1 dot 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 W naught transposed x xn. Now there are n plus 1 terms here. So we can safely say if each of these quantities is lower bounded by alpha, then this quantity W naught transposed W n plus 1 is at least n plus 1 times alpha, because alpha was the minimum of all these. So, therefore, this is at least n plus 1 times alpha. Okay, let us call this equation to be equation number 3. Now, what we have to focus is we have to somehow relate this in terms of the norms. So, therefore, we have to bring in another equality called the Cauchy-Schwarz inequality. So, let us apply Cauchy-Schwarz inequality to the left hand side of this equation that we wrote last, right. W naught transpose W n plus 1, I want to apply Cauchy-Schwarz inequality to this. So, for details of the proof of Cauchy-Schwarz inequality, you can look into one of the videos on YouTube. In fact, in the mathematical methods and techniques for signal processing course, I have proved the Cauchy-Schwarz inequality, and you can look into the proof of that inequality, or you can look into any other YouTube video or learning material. So, now what do we get? So, the norm of W naught square, this is the L2 norm, times the norm of W at time n plus 1 square, this is greater than or equal to W naught times W of n plus 1 square, right. A norm is a, it is an induced norm. So, it is basically W naught transpose W. Now, let us call this equation as 4, because on the right hand side we are trying to link this with n plus 1 times alpha, what we did, and that is the kind of idea how we are approaching this problem. So, from equation 4 and equation 3, the norm of W naught square times the norm of W n plus 1 square is greater than or equal to, and we have this bound, it is lower bounded by n plus 1. So, this square would be n plus 1 square times alpha square. So, I can write the norm of W n plus 1 square is greater than or equal to n plus 1 square times alpha square upon the norm of W naught square. I mean, if you are savvy, you will know that the W naught that you have is not an all 0 vector, right. You may say it is a divide by 0 problem, and that is a trivial case. So, you would not have the situation. Okay. Now, let us try to deviate slightly. We start with this recursion, but we had Wk plus 1 is Wk plus Xk and this holds for k equals 1 dot 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 till n for all x k belonging to class C1. Now, what we do is taking the Euclidean norm on both sides of this equation that we have, right. Taking the Euclidean norm on both sides of the above equation, we have norm of w k plus 1 square. So, this is going to be norm of the square. So, let us expand this out, right. We get this is going to be norm of w k square plus norm x k square plus 2 times w transpose k times x k. Now, this is very important for us, but since we are updating like this, our assumption is w transpose of k x k is less than or equal to 0 by assumption. Therefore, what we could write is norm w k plus 1 square is, because this is a quantity which is 0 or negative. So, the left hand side of this quantity here of this norm equation that I have in red, right, this is less than or equal to norm w k square plus norm x k square, right. Now, we have a sort of a recursive relationship in terms of the norms of these vectors. Now, we rewrite this carefully. Norm of w k plus 1 square minus norm w k square is less than or equal to norm x k square, and this holds for k equals 1 dot 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 till n, because we are sequentially presenting all these data patterns. Now, you recursively expand this out, it is straightforward. You will end up with norm w n plus 1 square is less than or equal to sigma k equals 0 to n norm x k square. Right, let us call this equation 6 and let us call this equation 7. Okay, this is straightforward, right. You take 2 minus 1, 3 minus 2, 4 minus 3 dot 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 as the index k is unfurling. So, you will just land up with w n plus 1 and then w 0, and w 0 is 0 vector. So, therefore, you land up with w n plus 1 norm square, and norm of w 0 square is 0 anyway. So, therefore, you have this summation of norm of x k square from k equals 0 to n. Okay. So, now we have to bound this somehow. So, let beta be defined as a quantity which is maximum over all x k belonging to class C1 norm of x k square, right. This is the other way around, I am choosing the maximum because I need a sort of an outer bound here. So, the norm of Wn plus 1 square is less than or equal to n plus 1 times beta. Now, let us call this equation number 8. Now, from equations 8 and I think it must be equation number 5 that I have here. On one side I say Wn plus 1, the norm of Wn plus 1 square is greater than or equal to some quantity. On the other side I say that the norm of n plus 1 square is less than or equal to some quantity, and there should be a point where it has to cross with equality, right. So, from equations 8 and 5, there must exist a n max such that it satisfies equations 8 and 5 with equality. So, we equate the terms. So, 1 plus n max square times alpha square upon norm of w 0 square must be equal to is 1 plus n max times beta. So, you can figure out that n max has to be beta upon alpha square norm w 0 square minus 1. So, you may be wondering, this has to be an iteration. So, therefore, you can kind of seal this function up to get a nearest integer, and then this quantity n max is going to be an integer. So, therefore, this implies a solution w 0 exists and the perceptron algorithm converges in n max iterations, and this should be intuitively obvious. So, I think because it is linearly separable, there should exist a hyperplane, and here by just adjusting the weight, by adding or subtracting a quantity, by balancing this seesaw somehow, right, we are able to settle to a value of n max which can terminate this algorithm, right. This is an important proof. Now, you may question how to start the algorithm, etc. So, one can start with any value of initialization w 0 equal to 0 or maybe a random quantity, and you keep iterating till you arrive at convergence. And you may also question, what about eta, right? Do we fix eta to be 1, or is there a way in which we can adjust this eta? You can always choose eta to be some small quantity also, and then you can proceed with the algorithm, and that should also settle this problem. Okay, so just small notes here. One can start with any value for the initial vector instead of fixing it to be the all 0 vector, because this is easy for us in terms of updating. So therefore it is okay to start with 0, but you can start with any value, and the other point is one can choose eta to be a fixed small positive quantity, right. You can choose eta to be a fixed small quantity, typically between 0 and 1, and still the update should sort of work. And in case you are finding that the update is basically going beyond any bound, then you can always normalize the data and get the algorithm towards convergence. So another aside, this is possibly from implementation standpoint of view. If you have a large number of data points, you can also normalize the updates and the data, so that the update rule is bounded. Okay, so you could do this also. But if you have large number of data points and you are sifting through one, and it is not possible, you can do this. And sometimes you can shuffle the data and also present it to the perceptron. Let us say you are in set of all points where you are only sifting through C1 and you are all correct, and then again you are going through C2. So you may want to have some variation to keep the weight not blowing up in a particular direction, right. So therefore you can kind of you can shuffle the data points also. So imagine you have an update equation where every time you have to add the point, you will end up in such a situation where Wn plus 1 is Wn plus Xn. So maybe you arranged your data in such a way that you are always adding these quantities, and it happened in such a situation. Then in such a situation you can always shuffle and present it so that you can get positive and negative signs around, so that it is kind of bounded, right. And the choice of the weight again is a question mark, because you do not want to have it to linearly increase, so you want to keep it bounded, and you can keep it normalized. So this is what I meant in terms of the practical aspects of this algorithm. So the best way one can exercise the algorithm is by coding it up, and you will see this through your homeworks. As you code the data points, you will know what exactly we are talking about in terms of the small algorithmic variations that we will have to do from the central idea. Okay, this completes the proof of convergence of the perceptron. Next we will look into the batch convergence, batch perceptron algorithm, and then the proof of convergence of the batch perceptron algorithm.